Okay, so now before writing for you the classification scheme for critical points, let me just explain a little bit of what the main idea behind it is. So in Calc 1, when you were trying to classify critical points as, say, local max, local mean, or neither, usually you had two options. The first option was simply to look at the first derivative and how it would change signs as you pass a critical point, say from positive to negative or negative to positive. Now, in our context, that's not that useful because, first of all, there's more than one derivative, right? There are two partial derivatives at least. And also, this is similar to the issue with limits, where there's like a lateral limit from the left and a lateral limit from the right. Now, there are many ways in which you could approach a critical point. Like you could spiral towards it and other things. So it's not clear what the right analog should be of like analyzing the changing signs for the first derivatives. So that's not the most optimal strategy. What's more convenient for us is simply to look at the second derivative test. And so if you remember, the second derivative test for a function of one variable said that if you had a critical point and the second derivative at the critical point was a maximum, right? Let's call it x sub c for critical. Then that meant that the function had to be a local mean at that point, and if the second derivative was negative at that critical point, then that meant that the function had to have a local max there. And one useful, so you said that the one useful heuristic for this is that well, you can make a phase where the signs of the i's are just the sign that you get here. And so if this is positive, you make two i's with positive signs, and so that means that you're happy, and that means that this is a mean. On the other hand, if this is negative, then you make i's with negative signs, so that means that you're sad, and that gives you a max. Okay, so that's a way to remember it. The reason why the second derivative test is true is that, say, if you had a critical point here, let's suppose that the critical point is at the origin, just because it makes things a bit easier. If it's not at the origin, you just move your coordinate system, you shift your coordinate system, and can analyze everything as if your critical point is actually at the origin. So if the critical point is at the origin, and you choose another point x here, right? Let's say that our function looks like this. Then again, by using Taylor's expansion, right, you would say that f of x can be approximated by f at 0 plus f prime at 0 times x minus 0, right? That's the advantage of using the origin as your reference point. You don't have to put x minus x naught here. Okay? Now, if you just keep the first order approximation in Taylor's expansion, this is not very useful because this being a critical point means that the first term, this term in the approximation vanishes. And so that means that you would be approximating the function with a constant function. That's not a very good approximation, so that's why you need to go to the second order term in Taylor's expansion. And that should be something like this, right? So you see what this says is that up to second order, right, the function looks like a parabola, right? This is like the equation of a parabola. This is just like a constant plus something quadratic. So that's the equation of a parabola. So that means that if this term is positive, right? If this is positive, then that means that the function at f of x, right, is a value at f of 0 plus some positive term, which means that this term is slightly bigger than f of 0, and that's why when this is positive, this point is behaving like a mean, because all points which are sufficiently nearby are slightly above it. If another way to say this is that if this is positive, then this looks like a concave up parabola, which is this, and so that's why you get the mean that we're talking about. On the other hand, if this is negative, right, then you're saying that the value of the function at this point f of x is the original value of the reference point minus some quantity. You're subtracting something now. So that means that f of x has been dropped down compared to f of 0. So that means that this slightly smaller value, and that's why in this case you would say that f of 0 is like a local max. Or in other words, this is behaving like a parabola where the concavity is negative or concave down, and so that's why you would say that the function has a local max there. And when the second derivative is 0, right, that's why we get something inconclusive, right? Because you need to analyze the cubic term in the Taylor expansion and other things, which we will ignore for our purposes. So what this means is that if we want a clue regarding how we should generalize the second derivative test to functions of two variables, for example, that means that we should look at the Taylor expansion for functions of two variables. So again, we can do first a trick where, say, if you want to, let's say this is the xy plane, and then the z-axis, right? And so the graph of the function, say, looks something like this. Now, so we're thinking that maybe there's some local max at the origin, and then the function will do its own things elsewhere. So again, similar to this, to the case of one variable, you can always like sort of shift your coordinate system if you want, so that in order to make things easier for this analysis, the critical point is taking place at the origin. Okay, so I have aligned my coordinate system so that the critical point has it's the origin. Okay, so here you have 0, 0. And then if you have a point which is sufficiently close to the origin, which is x comma y, we want to write an approximation for f of xy in terms of the derivatives of at the origin. Okay? And this is the analog of Taylor's expansion here. And so you see it would be that f of xy would be approximated by the value of the origin. And now you get the partial derivative of x at the origin times x plus the partial derivative of y evaluated at the origin times y. And so this is again the stuff that we saw earlier when we did the Taylor approximation, the linear Taylor approximation. The thing is, like before, I would write x minus x naught, right, or y minus y naught, because I was not taking x naught, y naught to be 0, 0. But the idea is that both of these terms, if the origin is a critical point, that just means that each of these two partial derivatives vanish individually. And then in particular, we need to keep going, because otherwise we would be approximating the function with a constant, which is something we don't want to do. And so you would put here 1/2. So, sorry. It's the same quadratic expression. It's just that now evaluated at the origin, x squared. Now there's a second similar term here. And then okay, so it's something regarding x related to x squared, right? So second partial derivative in x with x squared, second partial derivative in y with y squared, and then the mixed term with xy. The thing is that this appears twice, but since the partial derivatives commute, the mixed ones are the same. That's why you get 1/2 plus 1/2, which just gives you 1, and that's why there's no 1/2 in front of this term. Okay, and so the thing is, like, now we would need to analyze this an expression like this. Like, so the goal would be to analyze things like to analyze star this quadratic expression in the same way in which we analyze this one. Now the thing is that this one is very simple because it's just like x squared. Okay, x squared is just like a parabola. The thing is, like, now we can run into things which are more complicated. Like, we could have like x squared plus y squared minus xy, or x squared plus 3y squared minus plus 7xy. And so we need to sort of look at how all of these functions look like. We need to understand the graphs of those functions. And then, well, we won't get into the details for how we can do this, but the idea is that in the same way in which I could make a translation so that the critical point can be assumed to be the origin. The idea is, like, if you have the x-y axis, well, x, y here, and z-axis is my head, you can sort of rotate your coordinate system, and that's something that you do in linear algebra. You can rotate your coordinate system in such a way that these mixed terms go away. So the goal is to rotate so that xy is not present. Okay? So this problem about being able to rotate your coordinate system so that you can make the mixed terms go away is similar to what happens when you're trying to rotate a solid object. So there's a thing called moments of inertia, and the things that you could have, like, this solid object, like a book, and you can rotate it, say, about this axis. You could do a rotation like the one that I'm doing here. You could also do a rotation like the one I'm doing here. You can also do like a rotation like this one, but you could also do more crazy rotations. And the thing is, like, in general, for a solid object, there's this moment of inertia which relates the angular momentum with the angular velocity. And usually if you see a physics course, a basic physics class, they would write a formula like this. which would make you, this is a moment of inertia, that would make you think that the inertia is just like a number. But really, you should think of the inertia as a number just in a very specific situation, which is when you are rotating the body about what's known as a principal axis of inertia. But in general, if you're not doing, which are typically the ones that sort of respect the symmetry of the body. So for example, like the rotation that I'm doing here, like the axis is going here. But if you do something more weird, like rotating about the diagonal, which is not interacting nicely with the symmetry of the body, then this description still holds, but I will not be a number. It will become what's known like as a matrix or tensor. Okay? And so in physics you have this goal of trying to find which are the principal axis of a body, because that's where rotation becomes easiest and the inertia collapses to a number. And this is analogous to the problem of trying to find a rotation of my coordinate system that kills these mixed terms. So I'm just mentioning this. I'll make you watch a video, but I'm just mentioning this so that you know that really this problem is related to other more interesting problems. Okay? Sorry, there was a glitch, but I was just saying that once you know you can kill the mixed terms, then understanding what's going on becomes a lot easier. So there are just three things that can happen once you can kill the mixed terms. The first option is that your function looks like x squared plus y squared. In that case, that means that the origin, the 0, 0, is behaving like a local mean. The second option is where the function, this quadratic expression looks morally like minus x squared minus y squared. And that means that the function at the origin is behaving like a local max. And the third option is when the function looks like x squared minus y squared, or y squared minus x squared in the second order approximation. And this is the analog of what's known as an inflection point for functions of one variable, but what we call a saddle point here. I'll show you an animation in a couple of seconds so that it's more clear. But you should think of this as a like Pringles potato chip. So that means that there are just like some directions where you will see a max, and other directions where you see a mean as you approach the origin. Okay? And the nice thing is that we can distinguish between these three possibilities by just looking at an interesting combination of second partial derivatives. So that's what I will explain in the next video, but just wait a couple of seconds so that I show you the animation. So these are the local models that I told you about you can derive using the help of Taylor's theorem and the fact that you can kill the mixed terms. So the first one is x squared plus y squared, which is fairly easy to understand. So you see that there's a local mean at the origin. Okay, now there's the other one, which is the same model but with the signs reversed, so minus x squared minus y squared. And so you can see there that clearly that will behave as a local max at the origin. And the more interesting one, which is the Pringles potato chip, which would be something like x squared minus y squared. Okay, and this is the so-called saddle point. And so the idea, as you can see, is that, for example, if you're trying to approach the origin from this point, as you move towards the origin, you see a decrease in the function. So you, under this direction, you would conclude that the function is behaving like a local mean. On the other hand, if you approach the origin from this direction, you see an increase in the value of the function. So the idea is that with saddle points, depending on the trajectory that you choose to approach the origin, you either see it decreasing or increasing.